Hey, this is the Chapter 9, Segment 3 outline for behavioral neuroscience. For this segment, we're going to get started with electronic hearing aids. In electronic hearing aids, basic ones, a microphone picks up environmental sounds and amplifies them directly into the ear canal. However, this type of hearing aid can't help with sensorineural hearing loss, which is when hair cells or other neural components of the inner ear are damaged. However, with this type of inner ear damage, the auditory nerve can still be stimulated with electrical currents, and the brain can therefore interpret that as sound. This can be done by a cochlear implant, which provides a limited range of frequencies and loudness. This allows deaf people to be able to distinguish between voice and unvoiced speech sounds. Cochlear inputs have shown an increase in speech perception. Stimulation activates the auditory cortex in a tonotopic manner. This is why it's better to receive implants young so that they know how to interpret speech better. Now getting into the fact that fishes and birds can regularly produce new hair cells. However, this is not normal for really any mammals, except for in the organ of corti. The cells are capable of dividing and differentiating into hair cells throughout adulthood. ATOH1 can be inserted with the virus and has shown to result in the growth of new hair cells in deaf mice. The vestibular system, and now we're going to get into the vestibular system. The vestibular system detects position and movement of the head and affects balance. The vestibular system is part of the inner ear, and it is made up of 3 semicircular canals, which are fluid-filled tubes. The canals are on 3 different planes in which the head can rotate. Nodding up and down is known as pitch, shaking side to side is known as yaw, and tilting left to right is known as a roll. The canals are attached to a sac-like structure called a utricle, and lying below the utricle is another sac-like structure called the saccule. These organs are also known as otolith organs. The utricle and saccule provide remaining signals and are known as otolith organs. Each semicircular canal terminates near the utricle in the ampulla. The ampulla contains hair cells that signal movement in corresponding plane. The ampulla is embedded in the capula. Within the ampulla are stereocilia that have precise orientation and determine the direction of mechanical force. Getting back to the otolith organs, also again known as the utricle and sacrals, they have receptors that provide straight line acceleration and deceleration. And they can also increase the sensitivity of all of the other receptors in the vestibular system. Final part of the vestibular system are 6 muscles that control eye movement, and they must always counter the movement of the head. So that's why if you move your head around, you can keep your eyes pointed to one spot, and this is known as the vestibulo-ocular reflex. And we're going to get into some problems with having too much strong vestibular activation. Having too much strong vestibular activation can cause motion sickness. Just like this kind of explains why you would feel sick maybe while riding in a car for so long. This is due to movements uncontrolled by the body and also due to the sensory conflict theory. To explain the sensory conflict theory, it's also like why getting sick in a car, why people get sick riding in a car for a long time. It's because your vestibular system can tell that your body itself isn't moving, but yet you visually can see that you're moving because you're inside a car that's moving. In the sensory conflict theory, you receive contradictory sensory messages. And yes, once again, this is especially between the visual and vestibular information. The hypothesis is that stimulation is activating the system that originally evolved to get rid of swallowed poison. Basically, it's believed that back then it was to save us from neurological toxins, because if ingesting a neurological toxin can cause, symptoms similar to motion sickness at times. Another type of problems with too much strong vestibular activation happens with airplane pilots. This is a result of being inside the plane. Linear acceleration and upwards head tilt produces some stimulation in the otolith organs. This is known as the false climb illusion. Now we're going to get into taste, the sense of taste. The sense of taste provide an immediate assessment of food that is necessary for survival. Basically, we sense sweet because it kind of tells us that these foods are high in calories. We sense the savory because it tells us that this food is high in protein. Sensing salty and sour taste also usually can let us know that there are nutrients needed for homeostasis. And then the most important taste is bitter because it tries to alert us that what we're eating might be toxic. There's also something known as umami, which is known as the fifth taste in Japanese culture. This goes into how there's genetic variation across globe for strength and enjoyable qualities of various tastes. There's also another sense of taste called kakumi, which is the thick feeling quality of food, and this is due to calcium sensing receptors on the tongue. Now, taste is just known as the 5 basic tastes. However, sensations from complex foods like apples and steaks are known as flavors because you also need the sense of smell included. Now we're going to get into the structure that allows taste. We're going to start with the papilla, which are little bumps on tongues. You usually think that the little bumps on the tongue are taste buds, but it's actually the papilla. And the point of the papilla is to increase surface area on the tongue. There are 3 kinds of papilla: circumvallate papillae. There are very few of them, but each of them have a lot of taste buds. And this goes for also the foliate papilla. There's also a few of them, but they each contain a lot of taste buds. And then also the fungiform papilla, which only contains 6 buds each, and they look like button mushrooms. However, there are a lot of fungiform papilla. Each papilla has at least 1 taste bud. Each taste bud has 100 to 150 taste receptor cells. And at the surface end of each taste bud is a taste pore in which fine cilia extend from taste cells into pores. And this allows them to come into contact with the tastins, which is what the substance being tasted is. Taste buds only have a lifespan of 10 to 14 days, and each taste bud contains an immature taste cell that will eventually replace the taste bud when it dies. It's not really known what's the cause of such high turnover with the taste buds. It's usually just thought to be damage. All 5 tastes can be perceived anywhere on the tongue. It used to be believed that each section of the tongue had different taste receptors, but that's not true. Salty and sour are a result of taste cells being stimulated by simple ions acting on ion channels in the cell membranes. And sweet and bitter are perceived by specialized receptor molecules communicated by a second messenger. Getting back to salt, the taste of salt, once again, sodium ions from salty foods enter taste cells through sodium channels, and this causes depolarization within the cell and results in the release of a neurotransmitter that stimulates the afferent neurons. Another cause of the sense of tasting salt is a second salt receptor, which is a type of transient receptor potential vanilloid 1, which provides additional sensitivity to sodium, potassium, and calcium ions.